Hi guys, here we are. We've made it up to Oakey, just west of Brisbane, about 3 hours up in Queensland, and we're here at the OPEC PFAS water treatment plant. So it's a project we've been working on for really 4 years in the making, I guess, to get us where we are. We've started building about 6 months ago. It took us about 3 months to get the unit up and running, and we've been in commissioning phase getting it ready. So I'm joined today with Mr. Steve Phillips. Steve's one of the co-inventors of foam fractionation, and he's also been the driving force behind both developing the technology and getting it to a commercial stage here on site. So the Oakey plant is a 250,000 litre a day treatment plant for treating PFAS contaminated water. It's one of only 3 treatment plants that we're aware of in the country, and certainly in the world stage for PFAS treatment it's quite unique in terms of being a commercial full-scale plant. So we're going to run through a few things on the plant today to try and give you guys some education on how it works and what we've achieved. First stage we'll have a look at where we're drawing the water from and what we're treating. Second stage is we're going to run through the pre-treatment, so there's a little bit of prepping to get the water ready for fractionation. We'll then run through that fractionation phase itself. We'll then have a look at some of the dewatering and how we manage the waste, and then we'll look at the final polish before we're ready to discharge to the environment. So if you come with us, we'll take you through. Let's go. So we've made our way over to the well array, which is situated adjacent to the fire training area. So with the fire training areas, as probably most of you know, the PFAS used in the firefighting foam makes its way off the apron. Along with some other co-contaminants, it makes its way down, migrates vertically through the soil until it intercepts the water table, and that's when the trouble begins. That's what we're trying to deal with here at this hotspot. So we've got an array of 5 wells at the moment that are feeding our system. We're looking to expand that array over time, but Steve, perhaps you could just take us through the individual wells, how they're operating, what they're doing in there.
Yeah, so right behind us we've got a well. In this well we've got a compressed air system which is driving a submersible pump which is about 20 metres down in the well. That submersible pump is taking groundwater from the environs around the well, pumping it up through and down to the water treatment plant. The pump is driven by compressed air, and each pulse of air that goes through the pump pumps about 600 mils up and out. The air and the level of the water inside each well is monitored, and the information is transferred by optic fibre back through to our plant.
So you're controlling each well individually, you can see what the flow rate is, and if you had to, you could just shut the whole system down, is that right?
That's right, yeah.
So that winds us up here at stage 1 at the well array, so we might just head across back to the plant and we'll just start to take you through the finer details. So we've taken a bit of a stroll from the well array, which is about 400 metres to the north up here. We've got the 5 wells over there. We've directed the water over to this pre-treatment area where we get the water ready for the fractionation and subsequent polishing phases. So this really in our plant covers phases 2, 3, 4, 5 and 6. So we might just get a quick run through those, Steve, if you can.
Sure. So what we've got here is we've got the entry of the groundwater into the plant. Sometimes it contains suspended sediments that come out from the soil and the ground around the wells. And so that water comes into this large black 15,000 litre storage tank behind us with a sloping base, and in that tank a lot of that sediment settles out to the bottom where we can tap it off and take it elsewhere and dispose of it. After it travels through that tank, it comes down through the pipework here into what is called a coalescing plate separator, and this is quite an important part of the plant for reasons which Pete will explain to you right now.
The hydrocarbon issue is quite an important one, and it's one we'll probably come back to a few times through the presentation. The reality is, on these old fire training areas in particular, there's a lot of hydrocarbons get mixed up in the co-contaminants. And so, you know, you're using accelerants, you're using fuels to start fires, you're burning old vehicles. It's very common to have hydrocarbons commingled with your PFAS. So realistically, any system that is going to effectively treat PFAS from groundwater, it has to be able to manage this hydrocarbon problem. So we've put quite a lot of effort and time into a number of the phases that deal with removing that contaminant before we get to the resins. And the reason we do that is resins are very vulnerable to hydrocarbons, and so through the various stages, the coalescing plate separator and some of the later treatment phases, we're actually trying to extract both the free phase and dissolved hydrocarbons before they get to the resins, and that really optimises that resins. They're expensive, they generate waste. We want to use as little of them as possible, and so we're very focused on this part of it. The coalescing plate separator, fairly standard piece of industrial equipment, gets our free phase oils out down to sort of 10 to 30 parts per million. So essentially there's no visible oils or fuels on the surface of the water, and then we flick it onto our next stage, which is stage 4.
Yeah, and I might just add there that one of the main reasons we're doing this is right at the back end of the plant we've got some absorbent resins. They're very sensitive to hydrocarbons, so we really got to remove those. But the other thing about this back end of our plant, the resins, is they're sensitive to other materials as well, and there's iron and manganese and other multivalent cations will also clog up our resins and preclude them absorbing PFAS. So we want to get rid of those in this area as well. So in the next stage, what we've got is a large aeration tank here. So the water travels from the oily water separator, moves into this preliminary aeration tank. It's oxygenated, it's aerated, and in that process, the iron and the manganese are oxidised, and then they travel through the plug flow reactor behind the tank into these filtration banks in the 20-foot container next to us.
And this is really just to capture those precipitates that we've managed to get out of solution, and so we've got a series of diminishing bag filters starting at about 25 micron. We run that down to 1 micron. So really a lot of these suspended and solids that come in through the groundwater wells, by the time we get to the end of phase 6 here, we've removed those. We're ready to move across to the fractionator. We're finally at what we think is a really interesting part of the plant, because we invented it, so we really like it. But this is the foam fractionation phase of the water treatment. So foam fractionation of PFAS is a process that we developed and patented, as we said, over the last 4 years. Lots of hard work gone into it, and ultimately culminated in these units that you see behind you, which is stages 7 and 8 of the water treatment process. So Steve, give us a bit of a rundown. These are your babies.
Here behind me we've got 5 large black vessels. Within each of these vessels, 2,000 litres of water is processed over a 50-minute period, and in that time it takes the PFAS and strips it out of the water, and then that water that's driven off through the top of the fractionator goes to the following stage of the plant, with the treated water going through to the polishing end of the plant.
Yeah. So this stage is really interesting. It's a bit like if you imagine the pistons on a motor. We're sort of driving through 2,000 litre batches every 50 minutes, which is what's allowing us to achieve our 250,000 litre a day capacity. And we should say that that's based on a 50-minute processing time, and we're looking to reduce that significantly, maybe as low as 20 minutes, which obviously is going to enhance our overall capability.
And one of the important things about this process is there's nothing else added except air. So we've got this little motto that we've coined: air in, PFAS out.
And it's unique. It's the thing that actually separates us. So there's a lot of activated carbon plants and some really good resin plants, and while those products work really well, the mechanical, physical separation phase is what makes this really unique. So we're pulling out the PFAS as a hyperconcentrated foam. So to give an indication of that, we start with 20 parts per billion coming out of the wells. We finish our final stage at 2.5 million parts per billion. So the concentration steps throughout this process are enormous. This is the first of the concentration steps. It steps us up about a factor of 20
to 30 times.
20 to 30 times through the thing. So let's jump over. We'll have a look at the hyperconcentrator, which makes up the next stage, and is another concentration step, bringing it up about another 30 times again.
Yeah. Well, here we are at stage 8, which is what we've termed the hyperconcentrator, and that's the tank that's standing here right behind me. It's about 1,200 litres. It's currently operating in batch mode, and you can see up the top of the hyperconcentrator we've got a whole lot of water and foam swirling around. and it's in the hood where the action's happening. And you can see the foam being extracted by vacuum in the top.
This is probably for us one of the more exciting bits. This is where the patent and where the innovation lies. What we've managed to do is take this process of essentially air in and PFAS out, bubbles into water, and introduce with the right veracity, the right bubble size, the right sort of dynamics inside the vessel, and the right type of vacuum system, we're able to really efficiently harvest that foam out. So if you think in stage 7, we took a 20-time concentration step. Here we are at stage 8, so we've gone from 20 to about 400 to about 20,000 parts per billion at this particular water chemistry. So it's a fantastic step up. All of that before we've introduced any chemicals. It's all just a physical separation process. And so the hyperconcentrate we produce, we're then able to store and take onto our dewatering phase and produce a really minimal amount of waste. So let's jump up, have a look.
So though we're already about 10 or 15 minutes through this particular batch, you can see that the foam that's coming off right at the top there, it's a lot stronger than it was in the previous stage.
Yeah, so we're applying a constant vacuum onto this head, and then that's running down to a knockout drum in the next container where we're going to go in a minute, and then we'll see how we take that from there, dewater it even further, so we're getting absolute waste minimisation out of the original source water. We're really, we've treated already, you know, in a given day, 249 odd thousand litres goes through the system for initial treatment, and then it's polished. Then this system, the last couple of 100 litres, we're able to reduce that down to what is ultimately about 3.5 litres of waste per day.
And the 1,100 or so litres of water that's been fractionated in this vessel, it's almost to drinking water standards, but what we do is we take it and push it back through the system again.
Just as a precautionary thing, just in case. So the safety's quite important in this phase. We really need to manage the PFAS hyperconcentrate, and so we're starting to move towards dual skin pipes. We're starting to move towards minimising how far we travel it in the system, and we just bring it into the container right next door to this one, where we're going to move to now and just have a look at how that's done. Okay, so next stages I should say, 9, 10 and 11. So this is all about dewatering. This is all about taking that really beautiful hyperconcentrate that we've managed to get off the foam fractionation phases and then taking the water out of it. So effectively we got a few stages, mate. What comes first?
So right in the back end of this plant, we've got a holding drum where all the water's come out of the back end of stage 8. That's pulled through into a vacuum distillation unit, and it's there that that fluid is put under a very low pressure, and it's boiled off. The water is boiled off from the in a pressure chamber.
Yeah, at about 60 degrees we're doing that, bit over. And so what we get in that step is we get about 97% of the water comes out of that particular solution that we put in there. So here we go, third concentration step, another 30-fold. We're going from 20,000 parts per billion up to 600,000 or 700,000 parts per billion. So you can see we're really starting to get down to the business end here. And then we move on, final stage.
And the final stage is a drying unit, and this solution that we've gathered is starting to get a little bit viscous, and so we put it inside the drying unit and we dry it right out till it forms a sludge-like product. And one of the big advantages in this process is we're reducing the volume of and weight of the material that is a waste product, and so we're saving clients a lot of money in the disposal process.
So this last step, about another 30-fold concentration step, takes our final concentration up to around the 2.5 million parts per billion. So after treating 250,000 litres in a given day, we're now looking at about 3.5 litres of highly concentrated PFAS waste mixed up with a little bit of other bits and pieces along the way. But at about $5,000 to $8,000 per tonne to dispose of this waste, you can immediately see the advantages of this hyperconcentration process. It's fantastic. And so, and also all of that rich PFAS, now out at sort of 85%, 90% of what we were originally dealt with at the source water, is just here in the concentrate. We haven't had to put it through resins yet. We haven't even got to that stage. That's the next stage. So we'll go for a wander over there and we'll just show you this next and final stage of the process. Okay, stages 12, 13 and 14 of the OPEC PFAS treatment plant. You can hopefully just see down the back of the vessel there. This is our polishing phase, and in this stage we've got a couple of discrete elements that we work with. So what have we got here, Steve?
So what we've got here is we've got a lead and lag configuration of a couple of vessels which contain different sorts of exchange resins. When the water comes through from the fractionation vessels, it contains a lot of the small chain PFAS compounds, but it also might contain hydrocarbons, dissolved phase hydrocarbons, which are somehow not been removed in the fractionation process. So what we've got to do is we've got to remove those, and that happens in the hydrocarbon absorbent resin, and then the water flows through to a resin that is specifically tailored towards removing PFAS compounds. Now these resins, they're quite expensive. They're quite unique actually. They remind me a little bit of caviar.
Yeah, some selective resins that are really working on those specific contaminants, and we have to really nurture them along. A lot of what you've seen in the previous part is about protecting these resins. They're high cost and they're a waste stream. They're two things that we don't want to blow out for our clients or create for our clients. So this is the final stage. The hydrocarbon resin has a lead lag arrangement. The PFAS resin has a lead lag arrangement. It's just a sort of an extra precautionary approach in the event that you get some sort of breakthrough or there's some sort of breakdown in the resin materials. We've got a contingency and then contingency on contingency. So by the time the water exits this system behind us, it is sparkling clean, drinking water quality, ready to go back into the environment. And so just before we take that final step, we'll just run over to stage 15 here, which is just where we hold it and store it prior to discharge.
Okay, let's go. Okay, so here we are at stage 15, which is the final stage in the OPEC water treatment plant. And behind me here we've got 5, I think they're about 15,000 litre tanks, and each of these tanks stores the product that comes out of the back end of the polishing process.
So back end of stage 14, we've finished all of our treatment. It's gone through the final polishing stages, and we're just storing it here because part of our requirement with the client is just to make sure that we meet the drinking water guidelines. And in fact, our requirements are considerably more stringent than the drinking water guidelines. We're trying to meet about a third of the drinking water guidelines for our treatment process. So we're down around 0.02 parts per billion of total PFAS. So it's quite a stringent standard, but luckily we've been going now for a few months and we haven't once yet failed to meet that guideline. We are just inside the control room where we're going to have a quick look at something that I think is really exciting before we head over to stage 16. So this is where the brains of the operation are, not just Len Brown here, our operations manager, but also the PLC logic system that we've built onto the back of the plant. So the intention was, there's a lot of remote sites. We don't know where they're going to be. We don't know how many of these systems will ultimately be out there, but we want to be able to manage them, understand how they're working. And so remote telemetry was a really important aspect of that capability. So we've gone the extra yard on this plant. Every pump, every valve, it's all links back to this particular control center.
So we've got water in at the top right-hand screen. Inventory tells us how much water we've actually got on the plant at any given time. We've got the water discharge visible on the front screen as well, all the stages, and we've got some other reporting characteristics and a whole bunch of data tabs that we can get to, all from the screen itself. So for example, we can look up how much water came in today, how much we've pumped out, what our power consumption is, how many hours each one of those pumps has actually been running for. I don't have to be here to drive this. I can drive this from home by simply logging in, or I could be down in Melbourne or somewhere else in Australia or overseas, log in, and I can see that particular data as well. From here we can isolate all the wells, just a push of a button, we can turn them all off, or we can actually go out to the well, turn the individual ones on and off accordingly. Next screen, we've got water coming into stage 2, and you can see the transfer from 2 to 3 onto 4. We can see the volumes that are in the tank. All the data's in here necessary for an operator to very easily control the functions that are in here. Now, even though I can control it, the beauty is it's all automated. So unless there's an issue that springs up, such as low air pressure and the valves fail to open, for example, this plant will virtually run itself.
The point here is, through understanding the water in, the water out, the power, the waste produced, we're able to really accurately develop some metrics around the performance of the plant, the cost of the plant. So there's really two things that we're interested in. We're interested in the cost per milligram or gram per mass of PFAS removed from the environment, and the cost per litre of PFAS contaminated water treated. If we can harness those two metrics, we can really do some great comparison between different technologies in different parts of the world and understand the quantum of this problem and what it's going to cost us to resolve. So we've put a lot of work into being able to capture that data, and I think it's now that we're actually generating data on site, we're starting to reap the rewards of that. So, all right, so that was just a little side journey to show you through the brains part. We'll now head out into the bush, as I said, and we'll go and have a look at where that clean water is heading to. We're out in the bush. We're about 300 metres east of the water treatment plant. Behind us you can see some crystal clear water pumping out into the environment. So we're at the end of a very long, circuitous journey. Thanks for your patience. So we've now got this clean water, mate. What are our options?
Yeah, so we've got a few options. The first one that's being adopted here behind us is irrigation. So all the water is being used to irrigate the natural environment. We've also got another option of re-injecting this clean water back into the aquifer where it came from. And the other option we've got is reusing the water for construction purposes. So the water is safe to use, and it can be used for a variety of actions, including dust suppression.
Yeah, that's great. So it's a pretty good news story from our perspective. I'm really proud, mate, of you and the team and everything we've done over the last 4 years to get us here. We're taking 250,000 litres a day of contaminated water, and we're treating it down to drinking water guidelines. We're re-injecting it back into the environment. It's making its way back into the aquifer as crystal clear, clean water. It's a great outcome, mate. Good on you. Thanks very much. No. So that's it. Let's pack up our gear. We'll make our way back to Belrose and carry on.
Good one.